Alright, so this time we're doing problem 56 from chapter 4, and the question says, an object with a mass of m is at rest in equilibrium at the origin. At time equals 0, a new force is applied that has components. Force in the x direction with respect to time is equal to k1 plus k2 times y. And the force in the y direction with respect to time is equal to k3 times the time. It then says, components where it has these components where k1, k2, and k3 are constants. Calculate the position and velocity vectors as functions of time. And to do that, I'm not going to really do a whole lot of the math, but what we're going to do is we know that the force for both of these is going to be equal to the mass times the acceleration of k3 times time, and in the x direction, mass times the acceleration is going to be equal to k1 plus k2 times y. So from the beginning we can see that this function is dependent on the position of this function with respect to time. So we're going to solve this one first. So we need to isolate for the acceleration. So that's k3 times time divided by m. We then know that if we know that velocity with respect to time is going to be equal to the integral with respect to time of the acceleration dt. And so for this integral, everything except for the time can be taken outside the integral, and then the time is then evaluated. So that then gives us k3 divided by m times 1/2 t squared. We can then redo the same step to find the position with respect to time. With respect to time is going to be equal to our velocity, the integral of our velocity with time. So k3 m 1/2 t squared dt, and that gives us 1/6 times k3 divided by m times time to the third. Erase that, make it look nice. To the third, and that's our position. So we can then take this and substitute it for y in this equation. So this then becomes acceleration is equal to k1 divided by the mass plus k2 times k3 divided by 6 times the mass squared times t to the cubed. We can then go through the same process over here with this equation to find its velocity components. So velocity with respect to time is going to be equal to the integral of k1 over mass plus k2 times k3 times t cubed over 6m squared dt. You can then break these up into, use the addition of integrals to break these into separate integrals and solve for them individually. When you do that, you come to the solution that k to the 1 times m times t plus k2 times k3 times t to the fourth divided by 24m squared is our velocity component in the x direction. We can then find that the position with respect to time in the x direction is going to be equal to this, the integral of this again. So we take the integral from 0 to t, 0 to t, should be up there as well, of k1 t over m plus k2, k3, t4, t to the fourth over 24m squared, all of that before dt. You can then, once again, solve both of those as two different integrals added together and pull out all of the constants except for time. And that gives us that our position component is equal to k1 times time squared over 2m plus k2 times k3 times t to the fifth over 120m squared. It then wants us to give an equation for both the velocity with respect to time and the position with respect to time. So we'll do that now. And basically we've got an x component and a y component for each of those. And so it's pretty easy. So our velocity with respect to time, so these should all be in the y direction, and this should be in the x direction. So our overall velocity is going to be these combined. Is going to be equal to, we're going to add the k first, so it's going to be k1 over m times the time plus k2 times k3 times time to the fourth over 24m squared, and that's going to be our x component, and we're going to add to it our y component, so that's going to be k3 divided by m 2m times t squared, and that's going to be our y component. Our position is going to be the same thing, but with position vectors. So it's going to be k1 times t squared over 2m plus k2 times k3 times t to the fifth over 120m squared. That's going to be our I component for the position plus the y component of the position, k3 times t to the third over 6m, and that is our y component. So that's our position vector representation and our velocity representation.